All right, so this is Math 140, Calc 2. I've got it as 13. And what I want to do today is talk a little bit about review problems if we have time to do that. But I'm trying to keep one out of every third class as a class on application. And so there's, of course, a huge number of things I could choose to do for applications. I'm going to try to choose things that will allow us to review the concepts that we're doing and actually see them in practice. And then depending on how much time we have, that will affect the level of detail we can get into. We will do more on partial fractions on Wednesday. Oh no, wait, we don't have class on Wednesday, sorry, more on partial fractions on Friday. And so we are not going to just do one class on partial fractions. We'll do 2, maybe even 3 classes on partial fractions. It's one of the more painful integration techniques, but it is very valuable. These problems are challenging. How many of you have seen Zootopia? What's the best song for Zootopia? Try Anything. I'm not even sure if there's another song other than Try Anything. But for these songs, for these problems, what you want to do is you want to keep trying different things. If you think it's a U substitution, what are all the possible different things you can try? And hopefully one of them will work. The more experience you get, the faster it will be for you to see which is the right thing to try. If I really wanted you to become experts at integration, what would I do that I'm not doing? Or what would I do more than what I'm doing? If the best way is to get lots of practice, what should I be doing? More homework problems, right? So I could give you more homework problems, but then you have to do them. What can you do if I don't give you more homework problems? Yeah, just do some practice problems, right? Talk to me, talk to the TAs, talk to each other. Just do lots of practice problems. The more problems you do, the better. But this way, it's up to you. You don't have to do it, but the more you do, the easier it's going to be. And you'll start to get a sense of how to approach this. All right. So what I want to do now is I want to talk about the birthday problem. Has anybody heard of the birthday problem before in mathematics? You've heard of it. So if there's time later today, we'll go back and do some substitution. So how many people do we have to have in a row before we have at least a 50% chance that 2 of the people share a birthday? So any thoughts? I'm giving you a couple of possibilities. 11, 22, 33, 44 seems like multiples of 11 today, 90, 180, 365, or 500. Does anybody have a number that they want to vote either for or against? Yes. You're going to vote for G? Okay. And so I want at least a 50% probability. So is there anything that you think is either too low or too high? Why is 500 too high? How many days are there in a year? How many days are there in a year? Well, was it 365 or was it 366? 360. There's leap years. And so, again, I am not allowed to discriminate against certain categories. Being a Yankees fan is not protected. Being born on February 29th is not protected. And I have a deal with admissions that I am allowed not to teach anybody who is not. It just makes the calculation a lot harder if you consider somebody born on February 29th. Why is February 29th so bad? Yeah, it happens only once every 4 years. And because it happens only once every 4 years, what does that do? What's the issue? I'm sorry? Okay, good. So why is that a problem? That not a lot of people would be born on that. So what are you going to be assuming about the birthdays? They're what? They're on normal days, but more than that, that there's an equal probability of being born on any day, right? And so if we started to allow people to be born on February 29th, what does that do to the probability of everybody being born on the same day. So if we allow people to be born on February 29th, what's the issue? Yeah, and so we would not be able to have everybody born on the same, every birthday of the year being equally likely. And so what I'm going to do right now is I will just punch up in one of my favorite quotes from the book Outliers by Malcolm Gladwell. How many people have read Outliers by Gladwell? There's a great TED Talk. And so he substitutes the birthdays for players' names in the Canadian Junior Hockey Championship game. And it's amazing. March 11 starts on one side of Tiger's net, leaving the puck for his teammate January 4, passes it to January 22, who flips it back to March 12, who shoots point blank at Tiger's goal. April 27. April 27 blocks the shot. It's rebounded by Vancouver's March 6. He shoots. Medicine Hat defenseman February 9 and February 14 dive to block the puck, while January 10 looks on helplessly. March 6 scores. Which is really a shame because today's March 7. What do you notice when you listen to this? Besides, of course, my wonderful rendition. You notice anything about these dates? Well, January, February, March, you have a little bit of April, and nothing else. So Canadians and Canada, it's a very police state now. They actually have strict regulations on when you're allowed to have births. Why do you think there's such a disparity on days of the year for Canadian births in the Junior Hockey Championship? I mean, shouldn't people be equally likely that we're born anyway? Do you think hockey ability is tied to when you're born? Why? But shouldn't it balance out by the time you get to? So this is a great opportunity to talk about small bits of implicit bias, small bits of small asymmetries become significant. How many of you have ever played youth sports? Youth sports typically have a cutoff. If you are too young, you don't get to play. You want to be the oldest kid who just misses the cutoff. So odds are you'll probably be a little bit better than the people around you, because if you're a very little kid, those extra few months developmentally are huge. And so if you just miss one of the cutoffs, the likelihood is that you might be one of the better players. If you're one of the better players, what happens? Yeah, you might get drafted, you get more playing time, you get more training, and so that small little boost accelerates all the way up to the Canadian Junior Championship. And you can look at professional sports and you can look at the distribution. And again, it seems unlikely that people's hockey ability is strongly influenced by which month of the year that they were born in. But the way the system is set up, if you just miss, you become a little bit older, a little bit bigger, typically, and that small advantage lasts all the way up. So just something to think about how easy it is for there to be unintended consequences. So 500 we agree is right out because there's 365 for us days in the year. What about 365? Do you think that we need 365 people for there to be a 50% chance? What do you think? So is it possible with 365 people that nobody shares a birthday with anyone else? Yeah, how likely do you think that is? Very unlikely. Everybody would have to have a different birthday. What about 180 people? Do you think with 180 people, you're very likely to have at least 2 people sharing a birthday? Or do you think it's almost a certainty at 180? So let's look at the marginal person. A new person walks in with 180 people. What's the probability that they share a birthday with somebody already in the room, approximately? So if you have 180 people in the room, and let's say they all have different birthdays, and a new person walks in, what's the probability that they don't share a birthday with anybody who's already there? Around 1/2. What's the probability they share a birthday with somebody? Around 1/2. So if you take like 175 people, and 175 people, if you assume that no one shares a birthday, the next 5 people who come in each have roughly a 50% chance of sharing a birthday with somebody already there. So with 180 people, would you be surprised if no 2 people share a birthday? Yeah, I'd be surprised because at 175, if nobody shares a birthday, the next 5 people coming in, each one has roughly a 50% chance. So for them all to fail would be a 1/2 to the 30, would be 1/2 to the 5th, or 1 in 32. And that's assuming that the first 175 didn't share a birthday. So we're trying to just do some quick heuristics before we do the calculations in the math. Can we get a sense of the answer? This is the skill that will serve you in life. Partial fractions help. But being able to look at a problem and get a sense of what is the answer going to look like. With 180 people, I doubt it. I doubt I need to go that deep. What about 90? With 90 people, as a new person walks in, what's the probability that they share a birthday with somebody? Yeah, assuming that the 90 people already there don't share a birthday with anybody, a new person walks in, they're jumping, they're happy, they're joining the party. What's the probability that they share a birthday with somebody who's already there? Approximately about 1/4. So what's the probability that they don't share? About 3/4. So if I have 2 people walk in, the probability that neither shares is 3/4 times 3/4. So that's 9/16. That's close to 1/2. With 3 people coming in, the probability that all 3 of them fail would be less than 1/2. And so if I start up like around 85, and again do 5 people coming in, I see it's very likely that it's going to work. So in fact, I think these quick arguments show you that it's very unlikely that it's E, F, G, or H. What about 11 people? Do you think 11 people is enough so that 2 people probably share a birthday? $11 is less than what number? When you think of calendars, what number is close to 11 in the calendar? 12. So if I had 12 people, I would expect, yeah, I should have 1 person in each month. So with 11, I'm not even guaranteed to have 2 people in the same month, let alone the same day. So I think 11 might be too low. It's not a complete proof, but just, I'm not even at 1 per month at this point. So without doing the calculations, I think it's probably 22, 33, or 44. And again, we are assuming that everybody has an independent birthday. If we were looking at a meeting of the Canadian Junior Hockey Championship team after they won, I would not assume that the dates are randomly distributed and all dates equally likely. If there's a reunion on my wife's side of the family, given that she's an identical twin, I don't think all the dates are going to be equally likely. Whenever you have a problem like this, what you want to do is you want to gather some data. And so here's a plot. And so what I did is I did some simulations. I chose every day from 1 to 365 equally likely. And I just kept adding people until I had 2 people share a birthday. And then I stopped and I recorded what the value of n was. And I did this maybe 1,000,000 times. And I plotted what percent of the time I needed 10 people, what percent of the time I needed 20 people, and so on and so on and so on. When you look at this, what would you guess approximately? Remember, the numbers I gave you were 11, 22, 33, 44, and so on. So 44, to have a 50% chance. So if I take 44, that should be somewhere like around up here. So at 44, you have a near certainty. So I think 44 is a little high. Where do you think you need to have about a 50% chance? Around 22. And so years ago, anybody ever do WOW window on Williams? So I was asked to come and do a table for prospective students, and I had admissions agree to the following deal. If nobody among the students shared a birthday with anyone else, Williams College would pay for free admission for everybody at my table. Williams was a little bit concerned and said, I'll pay 10%. I gotta be careful because this is being recorded. I didn't tell my wife at the time that I was willing to do this. She's still my wife. I realized my wife at the time can be cost different. Why was I willing to do this? There were over 100 students coming. I showed admission. Here's the probability that we don't have 2 people sharing a birthday with 100. I mean, look at this, with 50 people, it's already near a certainty. With 100 people, not even close. So the students were extremely excited and they started going from table to table asking birthdays. They didn't even have to go to 2 tables before they had a match. It comes quickly. It's very surprising how quickly something like this happens. This turns out to be useful in cryptography. It's called the birthday attack. You can Google this and you'll find out how arguments like this are used to try to crack codes. One of the biggest things I want you to learn when you do mathematics is to generalize. So how could you generalize this problem? There's lots of different ways you could go. Can anybody give me one way, a related problem we could look at? What's a related problem we could look at? So you could do sharing a name. Let's keep it with birthdays. But you could do your people coming in with names and how many people do you need before you have a shared name? Yep, you could absolutely do that. And if we hopefully have a restricted set of names, and I believe Iceland actually has rules as to how you're allowed to name people. You can look it up. There's one country like, is it Iceland? Oh, do we? And then you have the artist formerly known as Prince, who changed his name to a symbol. So you could absolutely do things like names. What if we want to keep birthday? What could we generalize in this problem? Ways you could generalize. So you could go, how many people do we need before we have at least 2 people who were born in the same month? Absolutely. How else could we generalize? So instead of having 50%, I want to have at least a 90% chance. How else could we generalize? So what other numbers are in this sentence? Doesn't have to be 2. What could it be? Could be 3 people, 4 people, or I want to have 2 pairs where each pair has at least 2 people who share that birthday. There's another way to generalize. It really disgusts me how planet-oriented you are. It doesn't have to be on Earth, right? There's other planets in the galaxy. One of my former students actually has discovered a planet as part of his physics thesis at grad school. So let's go to Pluto. Oh, that's right. Doesn't have to be planets, I guess. Pluto has been downgraded. It is no longer a planet. It is a dwarf planet technically. But how many people do you need on Pluto before you have at least a 50% chance that 2 people share it? Pluto takes a little bit longer. Plutonian years, 248 Earth years, about 90,000 days. And so one of the questions is, how does 22 out of 360 generalize? So I can calculate the fraction of 22 out of 360. It's not a big deal. More or less than 1/10. 22 out of 360, more or less than 1/10. Less, 36 out of 360 is 1/10. More or less than 5%. More, 18 out of 360 would be 5%. So we know it's a little bit more than 5%, less than 10%. So just rough, quickly, you can try to roughly estimate it. So the problem is, if the number of days grows, how does the number of people depend on the number of days? Does it grow linearly? Is it just a constant multiple? Does it grow like the square root? Does it grow like the cube root? Does it grow like the logarithm? Well, we can do more and more data points. And so if anybody's brave enough and wants to try to guess, this is hard. What should we do? Check the data. And so if we look at the data here, where do you think roughly we need to get around 50%? Yeah, around 400 seems reasonable. Maybe a little bit less, maybe like 375, but something like that. And so if there's time later today, I'll talk about how you do the code. If not, we'll do the code at the next class when we review this. So I really want you to learn coding skills. Okay, so let's try to talk about this problem. So we could do things on Earth, or we could just do everything from the beginning and assume that there are D days in the year, and then just generalize and do all of them at once. People comfortable just doing D days in the year? And if you're having trouble with D, what should you just imagine in your mind D equals? So we want at least 2 B days the same. We have, say, N people, D days per year. So in mathematics, you want to figure out what is the right thing to calculate, what is the easy thing to calculate. Instead of calculating the probability that something happens, sometimes it's easy to calculate the probability that it doesn't happen. So if you know something doesn't happen with probability 60%, what's the probability it happens? 40. Now we're actually very lucky in that we're looking for how many people do we need to have a 50% chance. So the two of them are going to be the same. So let's calculate the probability no 2 people of N share a B day. Okay? So we want that probability to be about 50%. So if that is 50%, then probability at least 2 share is 50%. And when I say at least 2 share, I could have 3 people sharing, I could have 6 people sharing, I could have a triple sharing, could have a triple and a pair. What we're going to do is we're going to do something very similar to that marginal person we talked about before. When the first person walks in, what's the probability that they don't share a birthday with anyone else? 1. So the question is, how do we want to write 1? We'll start off by just writing it as 1. But we'll see in a moment that this is not the best way to write. Now the next person walks in. What's the probability that the next person doesn't share a birthday with the first person? Okay, so 364 over 365, or D minus 1 over D, right? Oh, well, okay, then how should I write 1? D over D. And in fact, it's going to be better to write this as 1 minus 0 over D times 1 minus 1 over D. And what's the last person, if we have N people, what's the last one? D minus what? Almost, but not quite. My son learned at a very early age that his dad is a mathematician and he could exploit that. And so when I would tell him you can do something 3 more times, he would say, that was my 0th time, Dad. How many times could he then do something? Oh, we're starting our counting at 0. We have 1 minus 0 over D. So if I were to do N things total, what's the last one? Could be N minus 1. So it's D minus N minus 1 over D. So it's 1 minus N minus 1 over D. And so I want to set this equal to 0.5. Find N so that this equals 0.5. Okay. Well, if you think about what's going on, if you take your calculator and you start multiplying 1 times 364 over 365 times 363 over 365 times This is a lot of multiplication to do. Okay. So we have 1/2 is approximately, I'm going to write it as a product. N goes from 0 to n minus 1, 1 minus n over d. So this means very similar to the sum symbol, this is the product symbol. This just means 1 minus 0 over d, 1 minus 1 over d, all the way up to 1 minus n minus 1 over d. It's an analog of the sum symbol that we've seen in Riemann sums, and it allows me to write a product very compactly. What should we do? You should be trained. I don't have my bell. What do you see here? What do we have on this page? We have it's not an interval. What is this? It's not a series. We're not adding a bunch of things. We're doing something similar. We are multiplying a product. We have a product. What's a Pavlovian reaction? Whenever you see a product, what should you do? Sorry? Well, Thoreau is to simplify it. So it's not, in some sense, it's simplifying, but there's a process we can do that converts a product to something nice for us, that we are more used to studying. You haven't done products before, you've done lots of stuff with sums. How can you turn a product to a sum? What can you do? Log. So this should be an instinctive reaction. Whenever you see a product, take the log of it. If you were teaching third graders how to multiply, bad idea. Other than that, it's a pretty good idea. Whenever you see a product, take a log. So then we would get the log of 1/2 is approximately the log of the product n goes from 0 to n minus 1 of 1 minus n over d. Well, that is the same as the sum n goes from 0 to n minus 1 of the log of 1 minus n over d. The log of a product is the sum of the logs. That's a great result to use. Okay? And so we can replace this product with a sum. Now, if little n is small relative to d, if n is much, much less than d, n over d is close to what? It's close to 0. So 1 minus n over d is close to 1, So the log of 1 minus n over d is close to what? 0. So we want to figure out how close. And this is where we are going to use Taylor series. And we're going to see more on this later in the semester. This is one of the big results. You approximate complicated functions with simple ones. So f of x is equal to f of 0 plus f prime of 0x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 x cubed over 3 factorial plus dot, dot, dot. This is called the Taylor extension, and it will converge in many situations. Or we can say f of x is approximately f of 0 plus f prime of 0 times x. This is the tangent line approximation. We can use the mean value theorem to show how close it is. Later, we'll use the mean value theorem to estimate error. Right now, we're going to just say, because n over d is small, we're not moving that far away from the log of 1. So the log of 1 should be approximately given by the tangent line. All right, so if f of x is the log of 1 minus x, what's f of 0? That's just the log of 1 minus 0, which is 0. What's f prime of x if f of x is the log of 1 minus x? So what's the derivative of the log of 1 minus x? Yeah, so first the derivative of log is the 1 over, so it's 1 over 1 minus x, and then we need the derivative of 1 minus x. And the derivative of 1 minus x is just negative 1, so this is just negative 1 over 1 minus x. So what's f prime of 0? So f prime of 0 would just be, negative 1. And so we get that f of x is approximately 0 minus 1 times x is approximately negative x. So the log of 1 minus n over d is approximately what? It's going to just be approximately n over d as x equals n over d. And we chose our function to be the log of 1 minus x. So the log of 1 minus n over d is approximately negative n over d. So when we return, so we have the log of 1/2 is approximately negative the sum, n goes from 0 to n minus 1 of n over d. What's the log of 1/2? The log of 1/2, that's the log of 2 to the negative 1. That's just negative log 2. So we get negative log 2 is approximately equal to negative 1 over d. The sum n goes from 0 to n minus 1 of n. Because each summand has a d in the denominator, so I can pull the d out. Okay, the negative signs cancel. I can put the d over on the other side, and I get the sum n goes from 0 to n minus 1 of n is approximately d log 2. And now I have to figure out what is the sum. So let's let Sn be 0 plus 1 plus, I'm going to do more generally. I'm going to do S sub m all the way up to m. So I'm going to sum the first m terms. Does anybody know the formula for the sum of the first m terms? Could you calculate if I asked you, sum the numbers from 0 to 100? Yeah. 0 plus 1 is 1, plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, this is 4. So the story is that when Gauss was 5, one of the greatest mathematicians of all time, the teacher was having a bad day and just gave the kids this problem to get some relaxation and get them out of their hair for a bit. And then Gauss immediately goes, 5,050. And the way Gauss did this so quickly is he noticed, well, let me write the numbers backwards. M plus m minus 1 plus dot 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 plus 0. And then if you add, you get twice the sum is equal to m plus m plus m. How many times do we have m on the right-hand side? How many times do we have m on the right-hand side? Nope. Let's look at the first sum. S sub m is 0 plus 1 plus dot 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 plus m. How many times do we have m? When we add things up, how many terms do we have in the sum? M plus 1, because we're starting at 0. We have m plus 1 terms. So twice the sum is equal to m times the number of terms m plus 1. So Sm is just m plus 1 over 2. So that means for us that this sum is going to be, here, we just take m to be n minus 1. So it's going to be n minus 1 times n over 2 is about d log 2. So n minus 1 times n is about 2d log 2, which is d log 4. And put the 2 inside the log. How would we solve for n? We have n minus 1 times n is a constant. How would we solve for n? So how would we find it? How would we solve this? What do you know that would allow you to solve this? What kind of equation do we have? If you view it as exact, solve n minus 1 times n equals d log 4. N is the variable. You've all seen equations like this before, but it's written in a way that you may not recognize. What kind of equation is this in n? It's a quadratic. N squared minus n minus d log 4 equals 0. An squared plus bn plus c equals 0. What could we use? Yeah, I don't want to use the quadratic formula. So what I'm going to do is I'm going to say n minus 1 times n is approximately n minus a half times n minus a half. That's going to be n squared minus n plus a fourth versus n squared minus n. I have n minus 1 and I have n. I'm just taking the point halfway in between. If n is of decent size, n squared minus n plus fourth is basically n squared minus n. And this allows me to bypass the quadratic formula. So I get n minus 1/2 squared equals d log 4. So what does n minus 1/2 equal? Yeah, it's going to be the square root of d log 4. So what does n equal? Almost plus a half. So it's going to be d to the 1/2, the square root of log of 4 plus 1/2. And so if I go to Mathematica, I do say f of d. I can't use a capital D because Mathematica has capital D assigned for derivatives. Is going to be the square root of d log of 4. So what do you think should happen if I put in 365? What should that be close to? Should be close to 22. 22.9944. So that's not bad. It's around 22 people is what you can. The answer is around 22, 23. Anybody remember how many days they put 20 in your head? Be more specific, 90,000. I believe it was 90,520. 354. It really is growing like the square root of d. And when you only see 1 or 2 data points, it's hard to sniff out that relationship. This is one of the great powers of calculus. We were able to estimate this and avoid having to do the painful multiplication. If you're doing that with a calculator, it's really hard. Which says, let's approximate this. So let's plot log of 1 minus x over 365. X goes from 0 to, let's say, 30. When you look at that plot, does that look like a straight line? Yeah, the changing line should be doing a terrific job. Let's go into 30. Let's go all the way up to 100. You see the curving a little bit? let's plot this against our tangent line approximation. What's our tangent line approximation? What do we approximate the log of 1 minus x as? The log of 1 minus x, we approximate that as negative x. So let's compare this to negative x over 365. And you can see, if I take x to be, 30 or less, it's very good. It's doing a wonderful job. Again, a huge amount is trying to figure out how can I visualize things. Instead of looking at it like this, rather than looking at the two functions, what could I look at? So if I wanted to try to see how close they are, rather than just plotting them together, what could I plot? Their difference. And so if I plot their difference, well, when I subtract, it just becomes a positive. And then when you scroll down, you can see the difference is extremely close to 0 as you go pretty far up. And instead of going all the way up to 100, what I'll do is for the second one, I'll just go up to 30. And again, you can see really, really accurate in terms of just how much of an error we're making. Another thing we could have done, let me go back to the screen, is we had the sum of n goes from 0 to n minus 1. And we said that this is n minus 1 times n over 2, which is approximately n minus 1/2 squared over 2. Imagine we didn't know that this sum happened to be n minus 1 times n over 2. How could we estimate that sum? What could we replace that sum by? So this is V1 sum. What could we approximate the sum by? Approximate by the integral from, say, 0 to n minus 1 of x dx. And what would that be? What function has derivative x? X squared over 2. So I could write this as x squared over 2 at 0 and n minus 1. So that would be n minus 1 squared over 2. So just, this is a class of integration. Let's at least do some integration today. Here's a way to evaluate that. Now, we also had earlier, we had, the sum, n goes from 0 to n minus 1 of the log of 1 minus n over, let's do 365. We'll do. So we might want to try to approximate that with an integral. So we might say, well, maybe this is approximately equal to the integral from, I want to write it as maybe the log of 1 minus maybe x over d dx. X goes from 0 to n minus 1. As a way to estimate. And now I have x over d, so I might want to change, maybe let u equal x over d. What would du equal? One over d, a little bit more, dx. So dx would equal d times du. As x goes from 0 to n minus 1, u goes from 0 to n minus 1 over d. So this would be the integral u goes from 0 to n minus 1 over d, the log of 1 minus x, so 1 minus u, du with a 1 over d outside. And then I would need to figure out, do I know an antiderivative for the log of 1 minus u? So you can see that by doing the Taylor series approximation, using the log of 1 minus x is approximately negative x, makes life easier. We don't have to figure out what function has derivative of the log of 1 minus 0. Now, we did do before the antiderivative of the log of x dx was x log x minus x. If you don't remember this, but I tell you that it's x log x minus x, what can you do? Yeah, take the derivative. We saw that one way to prove this was to write it as the log of x times 1 dx. And we had to say, what is u, what is dv? Well, if I choose dv to be log x, I need to find the antiderivative of log x, which is what I'm trying to do. Bad choice, right? So I have no choice. I have to make u be log of x, dv is 1, v is x, and then du is just 1 over x dx. So our integral is just uv minus the integral of v du. So uv is going to be x log x minus the integral of v du, which is just going to be dx. Because x times 1 over x is just 1, so we get x log x minus x. And that was a way to do it with u substitution. So you can then see, can you find an antiderivative for the log of 1 minus x? Or maybe you change variables. Let t equal 1 minus 0. We'll start with that. So I will just write, maybe set t equal 1 minus x and use next page. All right, so this is a good place to stop. I hope you got to see a little bit of some of the applications of what we're doing.